we thought we'd do something a little bit different and look at some application stuff that's been going on. So this is some work that I've been doing for about the last couple of years using OpenCL for molecular docking, which is all about taking atom level models of proteins and potential drugs and actually seeing how well these things fit together. So this is a molecular mechanics type operation. We're doing atom-atom force calculations. It's the kind of thing that pharmaceutical companies are doing, and the idea is to find the molecules that are the best fits, and if you find molecules that are good fits, then we may have found a really exciting new drug. We have a big molecule, which is something like a protein in the body, and we have small molecules, which are the kinds of things that would actually be a drug. So you might have 1,000 or 2,000 atoms in the proteins and 100 or so atoms in a drug. So we have a docking code in Bristol that we ported to OpenCL, and rather than just explain how it works, I thought I'd actually show you a little movie of how the algorithm works. So let's go all the way back to the beginning, and you can see what's going on. So we have the big molecule and the small molecule, and the game is to fit these two guys together. So we're just showing you sort of the end game. This is what we're aiming for, trying to work out what's going on. We've got to try and find the best place for the drug to fit into the protein. So that's kind of where we want to get to, and we can take a slightly different look at the protein. We can strip it back. We can try and spot the most important bits in the middle of the protein. But then what we do is we put a grid over this. We have some idea of where we think the active site of the protein is. So we don't have to look everywhere around this guy, and I'm going to pause here. And then what we do is we discretize this grid. So where the ligand molecule can go is on one of the grid points in this 29 by 29 by 29 at 0.1 nanometer spacing. Okay, so those are the points where we're actually going to see if these drug molecules go, which is lots of points, 24,000 grid points. We're going to search, and the other thing is each of the molecules, of course, can have a different orientation. So we take a molecule and it can spin around on its three axes at actually 10-degree steps. So that gives us a whole bunch of other possibilities. So there's 46,000 orientations. So we've got lots and lots of possibilities to try. There's a big number down at the bottom. And so what we do next is we have a genetic algorithm. Oh, let's sort of on this. Scroll that back slightly. There we go. So we have a genetic algorithm which generates a whole bunch of random poses. So we take the drug molecule and we put it somewhere and we rotate it by some random amount, and then we evaluate it to see how good a fit is this. And we're colouring all of these different poses from red is this isn't a very good fit to green this is great. So we're generating all these random tries, and all of these poses are independent. So how do we do that in OpenCL? We basically do a pose per work item. Okay, so this is how we go parallel. So we have massive amounts of parallelism here, which is great. We have lots and lots of poses that are all totally separate, so that we have loads of work items to throw at lots of different OpenCL devices if we have them. So this just calculates all these things in parallel, and then we look at which ones are best. This takes the 100 best poses and then generates random ones from those guys. Okay, so we starting to home in on which are the best poses, and as we go through each generation of our genetic algorithm, you see more and more green starting to show up as we find better and better poses, and we find better and better parents for a subsequent generation, and the whole thing starts to become a bit more sparse. And you see the whole thing's zooming on. So I won't let the thing run right way to the end, but it gets kind of slowly better, and you can see we're zooming in. So that's how the algorithm works. Okay. So how do we do this in OpenCL? Well, the first thing we do, we actually really run heterogeneously. So we find all the platforms we have in the system, and we find all the devices we have, and then we do some runtime adaptive stuff. So we actually run a micro benchmark. We take a few of our poses and we run them on every device, and we time how fast it runs. So now we've discovered every OpenCL device in the system, and we have some measure of how fast they all are and now we can do some load balancing. So we dynamically decide how much work to give each one of our devices, and every now and then, in fact, for each generation, we rerun the benchmark, just in case anything's changed. If there are some CPU devices we're using as OpenCL targets, OpenCL devices, maybe they've gone busy. So we just give it less work next time we rerun the benchmark, and it looks like it's slow, and we give it less work. So we've got this runtime adaptive load balancer in OpenCL. This is one of the things Ben was saying was might be really interesting. So a few other little things about the code. It's all single precision. It's massively compute intensive. We do very little data movement. That makes our lives much easier. This is kind of a really nice algorithm to do this kind of thing with. Very little data gets moved around. The protein's only a few thousand atoms. The drug molecule's only a few hundred atoms. You don't need much data per atom. And it's the same drug molecule everywhere, just with a different transformation matrix. So very little data. So it works really, really well. It requires very little compute on the host, so we can use the host as a compute device as well. So we run on everything. And what does this actually look like? Well, first of all, does it work? And we can take the kind of results we get from doing our simulations, and we can compare them to experimental results. So this is overlaying from X-ray crystallography with the results that we get, and actually it's pretty good. In terms of simulation, this is good enough. And in another example, again, this is the simulated result and the actual result. And in this case, turns out we were actually 1 grid point off. So that small distance, we were in kind of the right area and the right orientation, but we were 1 grid point off. Actually, for these purposes, that's good enough as well. So this is all looking pretty good. So now, the benefits of OpenCL, we can take this code and we can run it on almost anything, which we've been doing. So we have been benchmarking umpteen different platforms, and I'm going to zoom in on all of these a little bit more. The vertical axis is relative runtime, so shorter is better. The shortest are the fastest, shortest runtimes. So we'll zoom in on this. First of all, we'll look at the GPUs. So a whole bunch of different GPUs. We've got red for NVIDIA, we've got green for AMD. Fastest ones, there's little X2 that was using 2 at the same time. Okay, so that was the fastest. So your GTX 580 was nearly as fast as 2 Teslas, as it turned out, for our code. A whole bunch of different stuff, and an AMD one on the end. And we can do the same thing with CPUs. This is using the CPU as an OpenCL device. So this is effectively, instead of using OpenMP, using OpenCL to run on multi-core, and it works really nicely. And I've included, over on the left, that's our original Fortran code, which is pretty highly optimized, running on 8 cores of a fast x86. So 2 sockets of 4 cores each. So that's pretty much where we started, that 13.6. So the fastest platform we had was 13.6 times faster than that. The next bar along from the left is a very similar platform using all 8 cores, but with OpenCL. So the OpenCL was nearly as fast as the native Fortran, but it kind of gave us that parallel version for free, which for us is a brilliant win. We did the OpenCL to target GPUs, but now we don't have to do an OpenMP version to target multi-core. We get that coming out in the wash, which is great. A couple of different platforms, and we even have the one on the right. That's an AMD Fusion chip, just using the CPU. So not using the GPU, just using the CPU for a bit of variety. And then we can use CPUs and GPUs together because of OpenCL. And we are, so to come back to the portable performance, this is exactly the same kernel. We haven't tweaked the kernel, we haven't tuned the kernel, exactly the same kernel running on a CPU, a GPU, any flavor of GPU, and it's going pretty well. And maybe this might not be the same for everyone, but it can work out. So we have, over on the left, we have, that's 2 GPUs, 2 CPUs. Then we've got 1 GPU with 1 CPU. We've got the next one over with a speed of 2.3, that's an AMD GPU with an Intel CPU. And then at the end, we have a Fusion device where we're using the CPU and the GPU and the Fusion device all at the same time. Okay, all exactly the same OpenCL code. For us, this has been a fantastic benefit. I mean, we're kind of reaping the benefits of doing this stuff. And we look at not just performance, but also performance per watt. So we've been measuring power efficiency across all these different devices. Again, lower is better, okay? So we've got everything from over on the left, a single GPU, through to over on the right, 8 cores of x86 and everything else in between. And just to kind of pull out some specifics, we effectively started over here on the right, and we kind of ended up over there on the left, and we've been saving 88% of energy to do the same amount of work, the same amount of computation, much less energy, and much less time. A speed up of about 15 in this case, because it's a very compute intensive, it's not a bandwidth intensive app. And the thing over on the left is $500, so that's a good outcome for us. What does all this mean? Why do we care about this? We can save lives. So what we've been looking at is this protein, which is NDM1, which is a protein responsible for giving some bacteria the ability to resist antibiotics. So we're trying to find drugs that are going to treat that. We've used a really sweet big GPU cluster from Japan. This is Hamada-san's new cluster, which actually, it was in the keynote speech, the NVIDIA keynote speech. What he didn't say was the new version all uses AMD GPUs. Forgot to mention that, but we don't care, because we just run our OpenCL code on whatever they've got. It's worked fantastically well. We did 1 million dockings, and actually each one of the million had 20 flavors, so we did 20 million different dockings, which was 0.123 exa-atom energy calculations, which is quite a lot of compute. Hundreds of days of compute in 55 hours, and the results are looking really, really good, and it's all thanks to OpenCL. So we're actually using this, we're doing runtime load balancing across heterogeneous resources. Give us anything, different GPUs, different CPUs, we'll use it all efficiently. We're getting significant savings in terms of energy, as well as the thing just going really, really fast. We just couldn't have done it anything like as fast without using this. And we're finding for us it's working just as well for multi-core CPUs as GPUs. And the guys that we work with on all this stuff, it means they can now screen libraries of millions of potential drugs in 48 hours, in a weekend, on equipment that's hundreds of thousands of dollars rather than tens of millions. So, there you go.
Thank you. Any quick questions while we switch over?
Got a question here.
What hardware did you initially develop this on?
What hardware did we initially develop it on? We started off on effectively NVIDIA consumer graphics cards, moved to Teslas, realized they were actually quite expensive, and we've now been trying a whole bunch of really high-end consumer graphics cards, but also we're on whatever we can find. Yeah, seems to work well pretty much everywhere so far.
So in one of your performance results, the Fusion architecture actually performs really well. It's much, much better than the other GPU. As far as I know, I'm not sure which Fusion system you're using, if you're using the Nano, but the GPU is not as powerful as the NVIDIA GPU. And where do you think the performance comes from? Why is it significant performance different?
Yeah, actually, I think my bars are kind of the opposite way around to a lot of people, because it was runtime, so lower was better. So the Fusion GPU was actually higher up. What I didn't have, which would have been interesting, it was a Llano, by the way, would have been interesting to see the energy efficiency of that box, which should have been good. But that was the only one we were using remotely, so we didn't have access, we couldn't plug our energy monitoring equipment into it. So I don't have energy efficiency results for Fusion yet, although AMD have kindly sent me a box, which when I get home I should be able to try that and get some energy efficiency results.
But we have to continue, because I promised you we would be done on time, if not early. And by early I want time for just general discussion. So, Simon, you're not